So we're taking a look at number 15, and we have a charge configuration that is like this. And we want to know what is the net force, these are meters, what is the net force on each charge? The basic plan is easy. The execution is hard. The basic plan is I'm going to go to each charge and I'm going to represent the 1, 2, 3 forces acting on each charge, and I'm going to add them up. Ta-da! See? Done. But the execution is hard because I have to wrestle with some things. And what are the things that I have to wrestle with? Let's identify the things about this that make it relatively hard to do details-wise. What are the details that have to be nailed into place? Direction. Direction is the big one. And associated with direction are magnitude and, once I have the magnitude and direction, I'm going to have to find the sine and cosine components. That's right. Okay. And what else can make this challenging? Here's one thing that's seems a little silly, but often makes it challenging for students. Dealing with numbers in scientific notation. Times 10 to the, right? So the scientific notation can make it hard. These things. So, having identified the things about that make it hard, now let's focus on how we might organize these problems so that those things become not so bad. Does that make sense? As a smart problem solver, I identified the things that make these problems challenging, and I organize them away. All right? So how can I organize this? Well, one way that I can organize it away with regard to the scientific notation is that I can pull all of those exponents out to the side right there so that I don't have to sit there and carry them through in my computations. Would you rather deal with 0.003 or 3? Well, of course, with 3. So let's deal with the scientific notation by pulling that off to the side. And then in terms of components, maybe I can be smart about the components. All of the angles in this square are going to be either 90 degrees or 45 degrees. That's exactly right. And I know the sine and cosine of 90 degrees. The sine of 90 degrees is 1, the cosine is 0. And I know the sine and cosine of 45 degrees. They're both 1 over root 2. Yep. So I'm just going to leave those numbers as they are instead of writing them as decimal values. And there it is. And as far as the direction is going to be handled by our basic rule. Opposite charges subtract, and like charges with that in place. Now let's tackle this guy right here. Okay. So we're going to start with the charge at the top left just because it's at the top left. And we're going to say that the force on that charge up at the top left, let me call that guy Q1. And we'll go around the horn here. Q2, Q3, Q4 is going to be the sum of the forces from 2 to 1 plus 3 to 1 plus 4 to 1. And just by organizing it like that, I make it so that I don't have to, I make it so that it's less likely that I will skip one. Because I can count 1, 2, 3. Now, let's consider each one of these separate. The force from Q onto 1, in terms of magnitude, is going to be K times Q1 times Q2 over R squared. Okay. Now here, it makes sense to me that because I have 1, 2, 3, 4 charges that are equal in magnitude, I can just leave this as Q and fill in the 6 millicoulombs later. Which makes sense? Well, coulombs off. KQ1, Q2 over R squared.
No, yeah, I'm saying, what is that?
Oh, is equal to F21, the force that 2 exerts on 1, plus F31 plus F4. And it also makes sense for me to observe that all the distances are the same. So I'm going to call that R, and I'll fill in the 0.1 meters later. Now, I say all the distances are the same. That's not exactly true. If this is R, what is the distance across right here? If that is R, then it's R times, not times 2. Okay, guys. All of you guys have to do Pythagorean theorem.
0.14.
I mean, it's
Not 0.14.
it's R squared plus square root. I mean, that's a lot. Square root.
It's okay, guys. You're staring at me. You ought to be getting a piece of paper and scribbling madly. If this is R and this is R, what is that? Go. I'm appalled. I am. You guys all stared at me as if I was going to tell you. Yourself.
Square root. R squared plus R squared.
Which is the square root of,
2R
which is equal to what times what?
or 1.
No.
It works out with Pythagorean theorem.
It does work out with Pythagorean theorem.
So that's not the answer.
It is. You're just not evaluating it correctly. So you should all have this, but now how does that simplify?
2R.
No. It is R times the square root of 2. Yes. It is R times the square root of 2, which is not 0.14, but 1.414. Do something. Right? And this is a basic thing that you guys should know from geometry, certainly. So we have R root 2. Okay, so we agreed then that we're going to call those distances R, and we're going to call those charges Q, so that when I multiply Q times Q, I get Q squared. Okay. Now, let's come back to the question of direction. For that, we're going to have to use our hands. My force is going to be attractive or repulsive? Attractive. And therefore, the force on R1, Q1, is going to go to the right. So this guy is going to be all the way to the right in the positive direction. KQ squared over R squared, comma 0. Yep.
Is that F2?
Yep, that's F21. It makes sense for me to pull the magnitude to the outside and write this as magnitude times a vector that is in the direction of that force, 1 comma 0. Does that make sense to everybody?
No.
It makes sense for me to pull the magnitude to the outside and write the force as magnitude times a direction vector.
Yeah.
Vector in the direction. Using that concept of a direction vector is one way that physicists organize their work. How about F31? F31, that's the pain in the neck one. Skip it. We'll come back. F41. F41, I get to use some symmetry because because 2 and 4, same charge, located in relatively the same positions. The only difference is that one is located horizontally, one is located vertically. So the magnitude has to be the same, kq squared over r squared. But now my direction vector is different. Which way is that direction vector for the force on Q1? Going straight down. And so I can write that direction vector as 0, negative 1. Yes.
When you're plugging into the KQ1, Q2 over R squared equation, do negative signs, do you put in negative signs? 'Cause
No.
then the answer, okay.
No, because that would give you a direction.
Yeah.
And the direction happens with our
Okay.
rule, not with the signs of the charges. Yes, sir.
How do you get Q squared?
Because each one of these charges is either plus 6 millicoulombs or minus 6 millicoulombs. They have the same magnitude.
Oh, okay.
Yeah. So I'm just calling it Q.
Well, wouldn't it be negative? 'Cause you're,
That's what he just asked.
uh,
No.
I mean, I kept like,
No, because if you did, then you would be giving it a direction, and the direction of our force does not come from the charges themselves, but from our rule, opposites attract, like charges repel. Yes.
So, 1,0, how did you go about doing that new equation? You multiply-
Which way is that way?
Oh,
1, 0.
oh, okay.
Which way is that way? 0, negative 1. Yes.
Oh, that was my question for the 1 came from.
Yep.
Okay.
You want to think in terms of these direction vectors. All right, now let's come back and do the F31. The F31, same two charges, but my distance is a little bit different. It's r root 2. So I'm going to plug in. As kq squared over r root 2 squared. What about that direction vector? That direction vector is going to be the cosine comma sine component. And because the angle here is negative 45 degrees, well, actually, is that the angle I should be using? Let's think. First, hands. Which way is that force going to go?
it's gonna be trapped.
The force on Q1, which way is it going to go? It's going to go off to the left and up. At what angle? What is this angle? 135. That's exactly right. So my direction vector is going to be cosine 135, comma sine 135. And what is the cosine of 135 degrees? It is negative 1 over root 2. What is the sine of 135 degrees? It is positive 1 over root 2. Because the unit circle gives me a special angle sine and cosine.
you could also,
The x-coordinate on the unit circle is the cosine of the angle, and the y-coordinate on the unit circle is the sine of the angle. Have you guys done that in trig? You don't do that? Oh, yeah.
And then how did you get 135?
So, both of these charges here, Q1 and Q3, are negative charges. So the force between them is going to be a repulsive force.
Right.
So the direction of the force Q31 is going to be in that direction. Because it's a repulsive force. And I know the angle because since this is a square right here, this angle right here has to be 45, and that angle, of course, is 90, so that the whole angle from due east is 135.
So the,
I get 45. I can't see.
Let me do this down here. We've got the vector coming directly out of the corner like so, and we're looking for the angle as measured from due east,
Oh.
right? So there it is. If we were looking for this angle right here, which we would get when we were doing that guy right there, then that would be 180 degrees plus 45 degrees is 225. And if we were looking for this angle right here, then we would characterize it as either negative 45 or 315 degrees. And that angle right there would be corresponding. So this is a very useful concept. This is our direction vector. And it always has the value cosine theta cosine theta for whatever theta we got. And so it's very, very useful in characterizing the direction here. And that allows us to separate the magnitude from the direction. You see how that's a useful conceptual tool. Now let me simplify the middle term a little bit. The middle term is the only one that needs a little bit of special treatment. KQ squared. Hey, Corey. Thank you. We need some guidance. Okay, now here's where we get to be smart. This is the payoff. Does everybody notice that we have the KQ squared and the R squared as common factors of every single term? Factor them out.
I'm sorry, what? So,
KQ squared over R squared. Common factors of every single term. Factor them out. And when we do, we're left with this right here. And now we can actually go through and add. That's going to be 1, 0 plus 1/2 of negative 1 over root 2. You can work that out on your calculator. Should be negative 0.354. Because 1 over root 2 is 0.707, famous value that people know. Minus 0.354 is going to be 0.646.
Let's repeat. Let's pick the one.
I got the 1/2 from right there. We had KQ squared over 2R squared in that middle term,
Oh, yeah, yeah.
which is 1/2 of KQ R squared over R squared. KQ
Okay.
squared over R squared. Yes, ma'am.
Why is that an issue?
Way back when we found the distance from here to here, we found that distance is equal to R root 2. And when we square that distance, we get 2R squared. Or another way
So
of
when you
putting...
factor it out, you're left with 1/2.
Yeah, exactly. When you factor out the R squared, you're left with 1/2. So that as I go from here to the factored out form, I get 1/2, just like that. And now we're ready to actually plug in. We plug in 9 times 10 to the 9th, Newton meters squared per Coulomb squared, times our Q is 6 times 10 to the minus 3rd Coulombs squared, over R squared is 0.1 meters squared. And our force comes out.
comes out to 2.9 times 10 to the 7th conceptual direction. Or at least that's, I believe that's what the book said.
That seems a little high.
It might be. I think I was off by a little bit.
Because
16.
I'm getting, well, okay, so
Yeah.
we have 36 times 9 is going to be about 360. 10 to the 9th, 10 to the minus 6 is 10 to the 4th, 10 to the 6th.
2.96 times 10 to the 7.
Okay, yeah.
2.9 is pretty low.
Oh, was that the magnitude of the whole thing?
Um,
Yeah, well, let's actually do the computation.
well,
I got 3.24 times 10 to the 7 for the magnitude.
oh yeah, that's important.
Squared divided by 0.1 squared. So I get, yeah, 2.09 times 10 to the 1, 2, 3, 4, 5, 6, 7, comma, negative 2.09
Yeah, okay.
times 10 to the 7 newtons.
High five.
Yep. So this is the rectangular form. As far as I'm concerned, we're done. But of course, when you look in the back of the book, naturally, the back of the book is going to require us to put it in polar form. So that when we do, we get 2.96 times 10 to the 7th newtons. That's the magnitude. Can we be smart about the direction? I think we can. Because the direction, according to our calculation, is equal amounts to the right and down. What angle is that going to be? That's going to be at a negative 45 degree angle as measured from due east, or a 315 degree angle. Yes,
But isn't that still just for Q1?
that is just for Q1. So do we now roll up our sleeves and repeat these calculations for Q2, Q3, and Q4?
No.
Of course not. What can we do in order to,
Just change the bit.
we can just change the direction. What lets us do that?
How did you go? But then it's 2.86.
I just multiply them. Oh, here? By doing the rectangular to polar form that we've been doing since chapter 3. Yeah. I get a little fussy. I totally get it. You guys are working in an unfamiliar context with a whole bunch of scientific notation. So you're going, ah! Meanwhile, I'm going, guys, we've been doing this. So this is sort of an east meets west kind of a thing. You know what I'm saying? But
Such a long part.
trust me, I'm going to pull you into the west. So there it is. Okay, so speaking of symmetry, let's consider symmetry. Symmetry is a really powerful thing here. We have just discovered that the force on one is actually, the net force is actually pulling in this direction. Yes, sir.
How'd you get 135 for the angle? What was it, 145?
The original, this angle right here was 135 degrees, but the angle down here was 315. Yeah.
How did you get?
Well, because this is negative 45, right? And so if I go from due east counterclockwise, 360 minus 45 is 315. Yeah. So I'm just expressing it in proper polar form. If you told me negative 45 on a test, I would totally accept that. Yeah.
Something like doing the symmetry of the one from point 3 would be the same as the one from 1.
Yeah.
2 and
Right.
4 would be opposite.
Because of the symmetry of the situation, the force on 3 not only has to have an opposite direction, but it also has to have an equal magnitude. Because all 4 of these charges have the same magnitude and they're all the same distance apart. And I can look ahead and see that when I do the computations, these magnitudes are going to be exactly the same. The only thing that's going to change are my direction. And they're specifically each going to be 180 degrees opposite. So that when I add them all together, what I'm going to get for F3 is going to be 2.96 times 10 to the 7th newtons. But now, instead of an angle of 315, it's going to be at an angle of 315 minus 180, which is 135. And the same thing is true about F2. But we have to be careful how we think about the directions here.
Is the 209 times 10 to the 7 supposed to be 2.09?
It's 2.09 times 10 to the 7.
Yeah.
It's there, it's just messy. Yeah. That's mine. Bad handwriting. Now with the F2, we have to consider carefully. Are we going to get F2 pulling in or pulling out? It's pretty obvious it's going to do one of those. Which one is it going to be? How do you know?
Isn't sodium pulling in?
Why?
Because all of the forces are each point is being acted on in the same way. It's just rotating.
Very good. That's right. We have attractive forces happening along the edges of our square and repulsive forces happening along the diagonals, no matter which way we're looking. And therefore, this one is experiencing the same force as this one is, but turned by 90 degrees. So the force on it is going to be in, and the force on it is going to be in as well. What's this angle? F2. What's F2's angle? 225, that's right. So 180 plus 45. And what's F4's angle? 45. Oh, I said 6'9", that's 9'6". So that having done the hard work for one charge, we get to copy it all over and make it easy for the other three. Yes, ma'am.
That's the third problem.
The angle for the second one should be 135.
Not even 30,
No,
it
the
just took me a while.
225 and 450.
225?
Yes.
I don't think I even did it. I don't know.
It's better than I thought I had. I thought I was like completely wrong. I was just supposed to.
Okay. There is a moral, and that is that this problem right here, you want to consider probably the most detailed problem that you're going to encounter in this chapter, blah, blah, blah. For this one problem, I would strongly recommend doing it a second time so that you can think through the whole organizational piece of it. Notice what I did to make my life so that it wasn't completely horrific. I used symmetry to represent my charges and distances in terms of Q and R and factor them out. And I used direction vectors in order to separate the finding of the magnitude from the finding of the direction. And then finally, I used symmetry again so that once I had solved the hard problem once, I could recycle my work for the other three. That's crucial. That just cut our work in by a factor of 4. Yes, sir.
You can only do the symmetry thing if the charges are the same, right? Like the same
Yeah,
magnitude.
right. But when we look at number 17, which we'll look at briefly here, there are certain things that we still can do because of the symmetry. In 17, we have different charges, but we still have symmetric figures. Actually, why am I doing that? I should be doing this. There we go. So in 17, we have a setup where plus 4, minus 8, and minus 6. So we do not here have symmetric charges, which is really unfortunate. That means we're going to have different magnitudes for each one. But we do have symmetric direction vectors. Everything is 60, 60, 60. That's right. See? Equilateral triangle. So when I take a look at the 4 microcoulomb charge right here, even though I do not have equal charges all the way around, nevertheless, I can see for the 4 microcoulomb, attractive or repulsive, attractive, attractive or repulsive, attractive. So I'm going to have a force that pulls this way, and this angle is already known to be negative 60 degrees right there, which is the same as 300 degrees. And this force right here is going to be at an angle that is 60 degrees from here, or 240 degrees from due east, just like that. So that although I don't necessarily have the magnitudes, I can go ahead and do my direction vectors as cosine 300 and sine 300, and I can do my direction vectors here as cosine 240 and sine 240. And then I'll just have magnitudes that I can multiply by. Does that make sense? So the directions we handle separately from the magnitudes. That's the whole point of all this. These guys? Yeah. So this is an equilateral triangle, right? 60 degrees, 60 degrees. Draw myself a nice parallel right here. That's a 60-degree angle right there. So all the way around is 360 minus 60 is 300. And halfway around is 180 plus 60 is 240. You guys did angle chasing in geometry, didn't you? Yeah.
What was that cosine of 40 and sine of 40?
Cosine 240 and sine 240. My direction vector.
Oh, this.
Yeah. Once you have the angle from due east, your direction vector is cosine theta, sine theta.
I just thought those. So.
It's just me trying to write small. Poorly. Okay. Let's talk fields. That's our main lesson for today is electric fields. So we'll see what we can do. What we would like to do is to abstract the idea of a force by considering if I have a bunch of charges here. And I now place another charge near them. Then what I'm going to have is a net force which is going to be equal to the sum of all of the forces acting, which is going to be the sum of K times Q times Qi over Ri squared times the appropriate direction. Don't write this formula down. All I'm trying to do is to develop an idea. And the idea that I'm trying to develop here is that if I were to take out Q and replace it with a different charge, then all of these things would remain exactly the same except for the one Q. That's it. So we can think of all of this right here. Again, don't write this down. All of this quantity on the right here as something that is created by the charges Q1, Q2, Q3, Q4. And when I plop Q into that something that is created, a force happens. We're going to call that something an electric field. And the electric field is going to give us the magnitude of the force exerted on a charge when you put that charge into the field. So the picture then is that Q1, Q2, Q3, and Q4 are all going to combine together at this point to create some kind of, do it like this, create some kind of electric field that I'm going to call E. And when I put charge Q into that electric field E, a force happens. So here is the big equation that we're going to use that wraps up this whole thing right here. All of this sum is going to be called the electric field E. And E is created by charges when you place them into space. And the picture that we have, for example, if I have a positive charge Q1, is that that positive charge Q1 is going to create electric field all around it in every direction. Here I'm showing it coming out in the plane, but it's actually spherical. So it's coming out in 3 dimensions. That electric field is coming out from charge Q1, and if I place another charge near it in its field, like Q right here, then the amount of force that Q experiences is simply Q times field. And that's it.
That's
Times
the,
field.
wait, that's the net force.
That's the net force, right? So that is the big picture. I'm going to do a simple example. And what I'm going to do is actually push homework off so that tonight you can come back and take a look at just those 2 problems that we talked about today. And then tomorrow we can do electric field computations in earnest. Let's do a simple example right here. We're going to define, using Coulomb's law, the electric field exerted by a charge, the magnitude of that field exerted by the charge, as K times Q1 times the charge divided by the R squared. Notice what we're missing. We're missing a second charge, right? And we're missing a second charge because the field does not exert a force until you put a second charge in it. So what we're doing is computing the magnitude of the field created by a single charge. And if my charge is positive, then that field is going to be outgoing. Let me make this red for positive charge. And if my charge happens to be negative, then that field will be inbound. Like so. So let's actually do a computation here. Find the field at a distance of 0.1 meters away from a +3 microcoulomb charge. And so we're going to denote that field as E. And it is a vector quantity, but right now I'm just finding the magnitude. I'm not finding the direction for that field, because that direction is going to depend upon where you are. So the field is KQ over R squared. And now we plug in the numbers. Times 10 to the -6 coulombs all over 0.1 meters squared. And when we do, we should get 27 times 10 to the 3rd over 10 to the -2 times 10 to the 5th. So 2.7 times 10 to the 6th. What are the units? Meters squared cancel. one factor of Coulomb cancels, but the other doesn't, because we're missing a charge. So we get newtons per Coulomb. What does this mean? This means that we can draw ourselves an electric field around the 0.3 microcoulomb charge that comes out away from. Why is it out away from? Because we have a positive charge. And right here at a distance of 0.1 meters, the field strength is 2.7 times 10 to the 6th newtons per coulomb. Meaning that if I put a 1 coulomb charge in there, which is humongous, it would experience a force of 2.7 times 10 to the 6th newtons, which is approximately the weight of something that's several thousand tons. The unit is newtons per coulomb. So what we're going to do tomorrow is to explore this field idea in greater detail and ask what happens to our electric field when I place multiple charges near each other. Because the field is created by this charge. There aren't any other charges around as far as we know yet. Yep.